Okay, we should be live, and I think the audio is working. And so welcome to another live for Assumption of Physics, where we go in the detail in our work of ensemble spaces. So let me get everything right here. Okay, so a couple of things. Just to keep you updated to all the activities that go on behind the scenes. I have been revisiting the link between convex spaces and vector spaces with some mathematician here at the university. So that's probably something that we'll have to relook at. But long story short, the theorems that we had found that tells us when the convex space is embedded in the vector space is a little bit abstract. It uses a construction that it's abstract, such that we can't really understand how the topology of the convex space relates to the topology of the vector space. So I have been working on something that is a little bit more intuitive and grounded from the physics that it can be justified better. So hopefully when all of that is squared up, we can even understand whether we have a topological vector space or not, whether we need extra assumptions or not. So that's going on. And everything that I want to do is to thank Dante Broggi 3734, who left a comment on a live stream of a couple of times ago with a clear, stupid mistake in the proof that I fixed. So again, that's helpful. Like even it seems silly, but to make everything nice requires many eyeballs, and sort of this tells me again that doing this crazy thing of reviewing everything on YouTube can actually work and be useful. So, okay, so if there are no, so I have the chat there. I think I'm set up. So let me start sharing this as usual. So share the document. There we go. And let me backtrack a little bit. So we have our ensemble space. We have these three main axioms. One that tells us that since we have a connection to experimental verifiability, we have a topology, and the open set represent the statement that we actually verified with an experimental test. Since we have a set of ensembles and the statistical mixture of an ensemble of two ensembles is another ensemble, then we have a convex structure. So that's axiom 2. And then we have a third axiom that tells us that we have a well-defined entropy for each ensemble. Okay, so that's our starting point. And what we are going to do today, hopefully, we are going to look that these axioms by themselves, without any additional assumptions, allow us to create some measure theoretic tools that allow us to count state in the same way that we do in classical mechanics with area of phase space. We have something that it's similar to that, but again, on the general theory, without knowing that we have classical mechanics, quantum mechanics, and so on. So essentially, we are going to be creating an analog of the Liouville measure for quantum mechanics and beyond. That's the goal number 1. And goal number 2 is to create a generalization of probability theory that, again, works only on these assumptions. So the goal would be to have a probability theory that works in the same way in classical mechanics and quantum mechanics. That's the goal. And one can see if one tries to do that, you're basically going to require non-additive measure. That's basically going to be how it works. And again, the whole point of this is to have very simple definitions that are justified from the physics so that we know what we're talking about, and we're not talking about some abstract mathematical structure that we don't know how to think about, right? It's something that, again, can be justified from the physics. Okay, so let's start. And again, if there are questions on this topic in the chat, I'll stop and look at them. If there are questions on other things, I will be happy to answer them or discuss them, but at the end, once we have done the job for today. Okay, so we are going to talk about state capacity. So in this section, we're going to develop a generalization of the link between count of states and entropy. In classical mechanics, for a uniform distribution rho of U over a region of phase space U, we have that the entropy of rho of U is equal to the logarithm of mu of U, where mu is the Liouville measure that is taken to correspond to the count of state. This is sort of the very old ideas that Boltzmann came up with. If you have a region of phase space and you have a uniform distribution, so you don't know which one you have, the entropy is just the logarithm of the count of states. The idea is to generalize this relationship to all ensembles, classical and quantum. That's it. Given an ensemble, we want to quantify the number of distinguishable cases over which the ensemble is spread. Since entropy characterizes the variability of the preparation of the ensemble, greater variability means the ensemble is spread over more cases. Therefore, the count of distinguishable state must be a monotonic function of entropy. The question is what function? So, right, if you remember how we justified the axiom of entropy, we said every ensemble is a collection of preparations, and all these preparations might be different from each other slightly. And the entropy sort of measures how much these preparations are different from each other. And that's the only hint that we have that the ensemble actually correspond of a collection of other things, because we're not allowed to talk about other things, because otherwise we sort of have a recursion problem, a group of things and then are other things and then are other things. At some point we stop. So the fundamental token is the varied ensemble, and then the ensemble is this collection, abstracted collection on which we can write the laws of physics, because the laws of physics have to be a relationship between these procedures that we can always take. And that still there are some preparation, there is some variability, and the entropy characterizes the variability. So now we want to say, okay, it's a distribution, but how many cases how can we measure the spread? And of course, more variability means more spread, and so we need a function of entropy to be able to quantify in some sense how much these ensembles are spread. So the first hint that the exponential is the right function is the relationship rho entropy of uniform distribution equals the logarithm of the measure of U mentioned before, right? So this is a hint that probably the exponential, the relationship between the measure and the S is the exponential, because you take the logarithm and you put it on the other side, you get an exponential. Another hint is that we will want the size to be multiplicative over independent distribution. That is, if we have two ensembles, rho 1 from an ensemble space E1 and rho 2 from an ensemble space E2 of two different ensemble spaces, we can imagine the composite system rho equals the product of the two, representing the ensemble of two independent ensembles, while the entropy should be additive. That is, you take the entropy of the total ensemble is the sum of the entropy of the two independent ensembles. The count of states should be multiplicative. That is, the total spread of state over the joint distribution is the product of the count of state of the marginal distribution. So this suggests the relationship that the entropy of rho has to be the logarithm of the mu of rho for all ensembles. Now, the problem with this justification is that we don't have a full theory of composite system yet. And I'm delaying that until we make sure that everything else works in the single system and we can connect things to everywhere we want. But in principle, this is something that we should be able to argue at some point. The other hint is that the spread can be at most additive. If we mix two ensembles, the spread can be at most over the configuration of both and not more. And the following theorem, the following proposition shows that the exponential of the entropy has exactly that property. So even if we it's probably, if we can argue in a different way, we can argue basically if we have these two distributions and they're distributed in number of cases, the number of cases can at both be additive, and that might be enough to tease out that the exponential of the property is the only thing that has that property. Now, I should mention, and I mentioned it later, that for a series of circumstances, I was contacted by a mathematician. If I remember, the name was Michael Hall. He's, I think, from Australia, and he sort of arrived to the conclusion that the exponential of the entropy is the only measure of a distribution that can really represent a volume, that has the correct property of being a volume. So there is probably a very deep link with what he has been doing and what we're doing here. I haven't figured out all the details, but he also has an interesting uncertainty principle based on the exponential of the entropy that is stronger than the uncertainty principle that we have on the variance, because you can go from the uncertainty principle on the exponential of the entropy to the one from the variance. So his uncertainty principle implies the standard Heisenberg uncertainty principle, but you can't go the other way around. And so again, the idea that the exponential of the entropy is a very good a measure of the size of the distribution. It's something that's really the case. And again, if somebody wants to explore more of that and help me more on that, I'm happy to take all the help that I can get. But what we're going to do here is first to show, again, under very general term, without knowing whether we have classical mechanics, quantum mechanics, or whatnot, that if we have two ensembles, A and B, and E is a mixture of those two ensembles for some probability between 0 and 1, then the exponential of the entropy is subadditive. That is, the exponential of the entropy of E is less or equal to the sum of the exponential of the entropy of A and B. And the equality holds if and only if A and B are orthogonal to each other, so they maximize the entropy when they mix. And the probability that we put in front of A is the exponential of entropy of A divided by the sum of the exponential of entropy of A and B. And again, if you think about classical mechanics, these would be the two uniform distribution that you're summing, and you're summing them by saying by basically looking at the size to increase the entropy at most. So we're basically reverse engineering a lot of things that are there in statistical mechanics. Okay, so let's prove this, and the proof is nice because it's just calculation. It's very simple. And again, the fact that we can write such a simple thing on these very simple axiom means that we hit jackpot. So if P is fixed, the upper variability bound of entropy is saturated only if A and B are orthogonal by a definition. Therefore, the maximum entropy for the mixed ensemble will be achieved when the elements are orthogonal for some value of P, right? So if we want to see what's the maximum, it's going to be some value where they're orthogonal. Now we fix the entropy A and B so that we have some value as A and as B. This is just so that we can make the calculation a little bit easier to write. Now the expression of the mixture depends only on P, so we need to find the P that maximizes the expression. Since A and B are orthogonal, then we saturate the upper variability bound, so we know that the entropy of PA plus P bar B is equal to minus P log P minus P bar log P bar, and recall that P bar is just 1 minus P, so that we don't have to rewrite 1 minus all the time. And then there is the average entropy, so that there is the P, the entropy of A, plus P bar, the entropy of B, which is a smooth function of P. And since it is a smooth function of P, and we want to find when it's maximized, we just take the first derivative and we set it to 0. So we have that 0 is equal to the derivative of the entropy of the mixture, and we just substitute here, and we just take the derivative. So derivative of the product, so we derive the first part, the derivative of p over p is 1, so you just get log minus log p. We derive the second term is log p, the derivative is 1 over p, 1 over p simplifies with p, so you just get minus 1. And here you have the same thing, except then we're taking the logarithm of p bar. You have to remember that p bar is 1 minus p. So you're going to take the derivative of p bar with respect to p, which is minus 1. So you essentially have the same form of the derivative with a minus in front. Okay, and derivative of p is 1, so we just get SA and minus SB here. Okay, so that's what we have. And now we start doing this simplification with some tricks. So the logarithm here, we have the difference of logarithms, so that becomes the ratio of the logarithm, and it goes on the other side. So we have a logarithm of p over p bar. And then here where we're doing these tricks where we say that the S of A, the entropy of A, is the logarithm of 2 to the SA. And recall that all the logarithms here that we're taking are base 2. So, you know, since these two are one in the inverse of the other, this is equal to this. And now that we have a logarithm and we have a difference between logarithm, then also this we can use the quotient rule. So we have the logarithm of 2SA over 2SB, and we can express p bar as 1 minus p. And now we have two logarithms. The logarithms are going to be equal only when the two arguments are going to be equal to each other. And so we take this out of the logarithm. We take this part up here, this part up here. So we have this expression. We just collect p on the other side. So we have 2SB and then this 2SA that goes on the other side. And here we just have the 2SA. And so we find that p is equal to SA over 2SA plus S2SB. I always like how the math sort of dances around. It's always fun. But you see, there's nothing really complicated in this derivation. So now we know that the entropy of the mixture is maximized if and only if the two elements A and B are orthogonal to each other, and we're mixing them with this particular probability coefficient. So having found that p, the value of p that maximizes the entropy, we can calculate the maximum entropy. So we can go and calculate the entropy of the mixture, that is maximum mixture, in terms of the entropy that we found before. So first, we take a p bar, and p bar is going to be 1 minus p. And note that when we do this, we're going to take this, bring it up, and then subtract it. So the 2SA becomes 2SB, right? So again, fun. And now we're just going to calculate the entropy of the mixture just by substituting the p and the p bar inside the expression. Okay, so there was a p, we substitute the p's, substitute the other p, we substitute the p bar. We're just substituting the expression here. There is nothing that is going on. Now, what we can do here, and we're going to do here, is probably that some things simplify and some things we can essentially do products with them. So if we look at this and this, they have the same coefficient in front, right? So we can collect the coefficient, and then we have a logarithm here, another logarithm here, and there is a difference between them. So what we can do is flip the logarithm of this. So we take this minus and we flip denominator with numerator. And when we're doing the product, we're going to make the ratio between these two. And so this is going to cancel with the part that is on top. So we just have the coefficient outside with the logarithm of what was here that becomes up because the minus makes things go up in the logarithm. The same thing is going to happen between these two. Again, there is a minus between the two. The coefficient is the same. This factor is the same factor. There is the minus. We're going to switch it up. So what's going to happen is just that these go away, and we just have this expression. 2SA divided the sum of the exponential times the logarithm of the sum of the exponential entropy. And now, of course, we can take these two things and collect them. And what's going to happen? They're the same. So we're just going to have the sum of 2SA, 2SB. So this is what we have. And of course, these two things are the same. So they cancel out. So we just have that the entropy of the mixture is the logarithm of the exponential of the sum of the exponentials. And we do the same trick that we did before. The entropy is equal to the logarithm of the exponential of the entropy. And now we have two logarithms and the identity between two logarithms. The logarithm simplifies, and now we have just the identity between the exponential. Fine. Okay, so therefore the maximum entropy obtainable through a mixture is the logarithm of the sum of the exponential, which is obtained when A and B are orthogonal, and P is equal to the to this expression. So here we should say that we have proved that the exponential entropy, the exponential of the entropy gives us subjectivity. Ideally, we should prove that this is the only function with that characteristic. So I have a conjecture here, and I don't have a proof yet. And if somebody wants to figure out a proof, I'll be happy to take it. What we'd like to show is that if you have a function f that is a continuous function such that the function of the mixture of the entropy of the mixture is less or equal to the function applied to actually the sum of the function applied to the individual entropy, and the equality can be verified in some condition, then that f of x has to be an arbitrary constant kappa to the x. So I really strongly suspect that this is true, and it might not be even so difficult to prove, but I don't have a proof yet, and I have lots of other things to do, so I'm leaving it as a conjecture, hoping that either at some point I will have some idea and or somebody else contributes the proof. Oh, there is a comment that I missed. Maybe it's been so. Just to be super pedantic, technically, setting the derivative to zero just tells you you have an extreme or settled point, though it's easy enough to confirm that there is indeed the maximum. So you know that it's the maximum because the entropy is strictly concave. So you don't need to do it, but I guess we should probably say that, right? I can say that. We can say it at the end. No, we should say it here. Okay. So let's do it. Let's do it. Let's be pedantic. Note that since the entropy is strictly concave, the stationary point must correspond to a maximum. Okay, Pram, is that satisfactory?
Concave or convex? Sorry.
Concave.
Concave. Okay, good.
Right? It shapes like this, and so if you take 2 points, you can only go up.
Yeah, makes sense. Thanks.
Yeah, I always get confused a lot of the time when I write concave and convex, but I'm becoming better. Okay. Is it compiling? There you go. Okay, so we got that. Okay, so we have this very special property of the exponential of the entropy that becomes subadditive, and so it makes it has the right properties for a measure of volume, and we're just gonna assume that that's the correct one because of the link with statistical mechanics. So given a set of ensemble, we can ask what spread is reachable by a mixture in terms of number of distinguishable states. We call this the state capacity as it represents the maximum potential spread reachable by the set, and because it turns out to be a non-additive measure, and footnote tells us in some literature capacities are non-additive measures. The state capacity is monotone, subadditive, and covers the additivity over overall set. So basically, what we're going to say is we kind of have quantified the spread of a single ensemble. We take the ensemble, we take the exponential of the entropy, and we say that that's a measure of how much that ensemble is spread. And now the idea is that we have a set of ensembles, and what is the biggest spread that we can have as a convex combination of those ensembles? So what is the maximum spread that we can reach just by making a convex combination of that? And so in some sense, it tells us how many configuration, how many states can we spread things starting from a set of ensemble. So we define the things in this way then. Let A be a subset of an ensemble space. Then the state capacity of A is defined to be the superior of the exponential of the entropy of the hull. So the hull, if you recall, is the set of all the possible convex combination that we can make starting from elements of A. So you take all those possible convex combination. You take the entropy of all of them, and then you take the exponential of the entropy of all of them, and you take the supremum, so you take the highest possible exponential entropy that is reachable from that set, and you call that's the state capacity. That's the maximum spread that we're going to have by combining things in that subset of the ensemble space. Now, this union zero is there such that I don't need a separate definition for the empty set. So if these were the empty set, this would be the hull of the empty set would be the empty set. The exponential of no element is nothing, so I would have the empty set, and the supremum of the empty set is not defined. So I stick in a zero. Now the supremum becomes the supremum of zero. So I have the state capacity of the empty set is zero. There are no states in the empty set. So it's just, again, the mathematical thing where you have to make sure that your extreme cases work in a decent way. Okay, so from this definition, then it's at the end of the day, it's not very difficult. We just get all the exponential entropy that we get from all that. We can prove this nice feature. The state capacity is a set function, meaning that it takes a set of ensembles and it gives you a number. And that set function is non-negative, meaning that it returns a number from 0 to infinity. And the proof of that is simple. The state capacity takes a subset of E and returns a real value and is therefore a set function. And the exponential of the entropy can only return non-negative values. Therefore, the state capacity is a set of non-negative value. And again, if you think of the Liouville measure, you take volumes of phase space. Well, volume from a space can be from 0 to infinity. If you take the whole thing is infinity, if you take the empty set is 0. Right? There can be a region with negative amounts of state, and so we get that. The state capacity is monotone, meaning that if you have A that is a subset of B, the state capacity can only be bigger for B. It can't become smaller. So the state capacity of A is less or equal to the state capacity of B. And again, this is simple to prove. The hull is a monotone function. If you start with a set and look at the convex combination, if you increase the size of the set, you still have all the convex combination that you could do before. So the hull, the convex combination that you can get with more things is just more convex combination. So the set can only grow, is a monotone function. The image of a set through a map is a monotone function. Again, if you have a map that you're applying to a set of things and you get a set of value, the set of possible values cannot decrease if you increase the size of the set. So it can most stay the same. And then the supremum is also a monotone function. Like if you have more numbers to find the upper bound can only go up, cannot go down if you increase the number of things. Therefore, the state capacity is a monotone function. So that's it. And this, again, is nice because all the measures that we have basically everywhere are monotone functions. If you have, again, the Liouville measure, you increase the size of phase space, well, the volume can only increase. So that's good. It's going to be subadditive. So if you take two regions, right, and you do the union of those two regions, then the state capacity can only become at most of the sum of the two regions. Again, if you think about measures of volume in phase space, you have two regions, and you ask what is the total volume of the region, of the union of those two regions. Well, at most can be the sum. It can be it's going to be less than the sum if you have some overlap, but at most can be the sum. And again, this is knowing what we proved before. This is not very difficult to prove. So you have A and B that are a subset of E, and you take a convex combination of A and B for some P. A is in A and B is in B. And by what we proved before, and the definition of state capacity, we have that the exponential of the convex combination can only be up to less the sum, and then these two are actually the state are going to be bounded by the state capacity. So this we get from the previous theorem, and this just by the definition of the state capacity, because this has to be less than this, and this has to be less or equal to this. And now, since this is true for any finite mixture of elements of A and B, it will also be true for any element of the hull of the union, since the entropy is continuous. And consequently, the supremum of the exponential of the entropy cannot exceed the sum of the state capacity. Therefore, the state capacity of the union is less or equal to the sum of the state capacity of the individual set. So, good. And then the other thing that is interesting and crucial is that if we have two sets that are orthogonal, and recall for us orthogonality simply means when we put things together, the entropy is maximized, the increase of entropy is maximized. Then if two things are orthogonal, then the state capacity of the union of the two sets is equal to the state capacity. So in measure theory, you have the typical when you have ideas of measures when we have two sets that are disjoint in a standard measure, you have additivity. You have two disjoint sets, and the measure is the sum of the measure on the two individual sets. Well, here is not it's not that the set have to be disjoint, they have to be orthogonal to each other. So this orthogonal is a stronger condition, where now we could have two sets that are disjoint from each other, but then the state capacity is not additive. The two sets have to be orthogonal. You have to have the ensemble maximize the entropy when put together. And again, to prove that, we can just reuse the theorem that we already proved before. So you have A and B, and these are two orthogonal sets. And you take AI to be a sequence of ensemble such that the entropy, the exponential of the entropy of the sequence becomes converges to the state capacity. And the same thing happens with the BI. BI are such that they converge to the state capacity. So you basically have two sets, and you have two sequences, and these two sequences essentially approximate more and more the maximum entropy that you can have. You have to do a sequence because the entropy could become infinite, right? So if you have, let's say that you take phase space, you divide it in two parts, right? You can get a distribution that is spread over a bigger and bigger and bigger area on one of the half plane, and so the entropy will go up and up and up. So you're never going to reach an infinity, right? You're never going to find a distribution of entropy that has a uniform distribution over an infinite area. You're not going to be able to do it. But the entropy, the maximum of the entropy, the supremum of the entropy is infinity. And so what we're going to make sure here is that this proof also works in that case. So we can't just say we pick the ensemble that has the supremum of the entropy, because that might not exist. Okay, so we take these two sequences, and now we make the convex combination of the two sequences. And again, we set the PI to be that proportion that we found before. Then by the previous theorem, what we find is that the exponential of the entropy is equal to the sum of the exponential of the entropy of A and B for every I, which means that now the exponential of the entropy of EI converges to the sum of the state capacity. And therefore, the state capacity must be at least the sum of the two. Now, we know from before that the state capacity is always at most the sum. So we have to be at least the sum, at most the sum. The state capacity is going to be the sum. And therefore, the state capacity of a state function is additive over orthogonal sets of ensemble. Again, the cool thing here, I'll say it a million times, is that we don't know what state space we are in. We don't know if we have classical spaces, quantum spaces. We don't know anything, and we just know that this definition works in a very general way. And so I would hope that at some point these things apply also for, say, a classical field theory or a quantum field theory, such that we can talk about the count of configuration for fields, and we have a better understanding of how the entropy works there and so on. That's all area that I haven't explored yet, because again, I want to make sure that everything works in the simple case, and then you generalize, because if you generalize before knowing that things work in simple cases, you're just gonna get confused. So I want to make sure that this works there, and then we are gonna make sure that this also works for the cases where we have no idea how they work. There are two conjectures that I have not proved yet. Again, this tells you that this is a work in process. The state capacity is continuous from below and above. I think this is true. I think it's going to be simple to prove. I just haven't done it. Continuous from below, from above for a set function means, so you have a set function. So you take a set and it gives you a number. And now you take let's say a decreasing series. You take the sets, the sequence of sets that becomes smaller and smaller, so that each set is contained in the previous set, right? So you approximate your final set from above, because you're approximating with bigger set. You take these bigger sets, and at the limit, you're going to find what is your limit set. And the idea should be then that if you have such a sequence, the limit of the state capacity is equal to the state capacity on the limit. So if you take all the state capacity at each step, you're going to converge on the state capacity of the final element. And again, I think this is going to work. It's just a matter of proving it. And the same thing is going to be from below. From below, you have the set, and you start from inside, and then you grow your set until you reach the final thing. These are standard techniques when you do measure theory, and therefore when you do probability theory. A lot of proofs are based on this idea of continuity from above and continuity from below. So the thing that why this is important is that this would allow me to hopefully generalize these two expression to a family of sets. So right now I'm just saying that this is additive over when I have two sets and I do the union of two sets. If the state capacity is continuous from above and from below, then what's going to happen that this is going to work also for the union. I think I actually need only from below to be able to prove that that's going to be the union. So once you have that, it's kind of like you have the sigma additivity that you would have for measures. So typically in measure theory, you assume the additivity over the infinite countable collections, and then you prove continuity from above, from below. What we have found, especially because we have non-additive measures in the general case, it's easier to do the opposite. You assume additivity or subadditivity for finite, and then you check that you have continuity from above and below, and then you recover the sigma additivity and the sigma subadditivity. So this is again you have to find the right way at the mathematical level that sort of is more convenient to make all these proof work and all these things work. Okay. The other thing that I have not proof, at least I have some beginning of the proof, but it's actually not a proof. I have a conjecture that the state capacity is only additive on orthogonal sets. So you should be able to go in the other direction, so that if you know that the state capacity on the union is the sum of the state capacity, then you should be able to say, oh, okay, these two sets must be orthogonal. And there is a little bit of a detail here that this sort of made me realize there are probably more things that couldn't be proven about orthogonality and so on. So let's just prove this is a proof of a conjecture. It gives you some of this idea. If the state capacity adds, then the state with the highest entropy satisfies the upper variability bound and are orthogonal. What needs to be shown is that this is enough to say all elements are orthogonal. This is the part that I'm missing. And there is possibly a series of nice results here. If A is orthogonal to B, then A is orthogonal to all the components of B. So this is essentially what we are saying. If this is true, I need to prove that. And if A is the ensemble with maximum entropy in the hull of A, it should be true that all the elements of the hull are components of A, right? So if I'm making the maximum entropy spread, that anything inside the set where I'm constructing the state with maximum entropy should be a component of that. And again, this makes sense classically, right? If I have a region U and I take all of the possible distribution inside there, right? And I take the biggest one. The biggest one is the uniform distribution. And the uniform distribution can contain as a subcomponent any possible distribution, because you can take any possible distribution, shrink it down below the uniform distribution, and then you can say the uniform distribution is the sum of that shrunk down component plus something else that is still inside you. And again, this is kind of fun when doing these things, is that trying to prove other things gives you insight on actually more fundamental property of the objects that you had defined before. And that's sort of how you learn how the objects actually are, just by looking at the definition. It usually doesn't tell you much. But so this would be something that is probably provable and probably is not even going to be that much work. But again, I am doing right now other things. So if A is the ensemble with maximum entropy in hull of A, it should be true that all elements of the hull are components of A. If one ensemble is not, we should be able to create an ensemble with higher entropy. So I think you should be able to prove it by contradiction. Okay, so that's basically it. And this is what I was saying before. Note that the state capacity for a single element corresponds to the ensemble volume defined in this work and more recently here. These are two papers. I think this is from 1999. This is a little bit more recent. And again, I don't know why these results are not more widespread. Sometimes I feel that, like, a lot of the time, yeah, I don't know. It's important results like remain obscure and they get rediscovered over and over. And then like things that are even wrong gets repeated, and people always learn the wrong things and then have to unlearn. I don't know. That's how it works. So it is connected to various uncertainty relationship, including a stronger form for the quantum uncertainty principle. And again, it would be interesting to understand what results can be generalized to the ensemble space. Like this is basically what we want to do in this work, not only just give a common foundation to everything, but try to find as many results that we can and stick them inside here. I think he also had a connection to the Holevo bound. So if there is a way to sort of get these bounds already without knowing whether we have classical mechanics or quantum mechanics, that sort of would be good. But I think we need a notion of product spaces to be able to do that. But again, at some point we'll get there. Just style-wise, I think I'd prefer it if you use the citation name, like, I don't know. Yeah. Uh, the whole text needs to be adjusted. So right now, my concern is just to have links that are clickable so that you can go and see where things are. And the reason is that the text right now is not even very didactic, and it could be improved in a lot of ways to be more explanatory. In fact, you know that I always stop and try to give more context because it's very terse. And But we're going to do that at the end, because what happens over and over is that I am reshuffling things around based on the math. So what happens is this: you start with an idea, right? And you say, okay, I want to prove this, this, and this, and then you write, oh, actually, it would be better to prove this before that section, right? Because things that I'm proving here are actually important here. And so there is constant reshuffling, and the prose, I think, makes sense to write and finalize only when we have a good idea of what is the overall structure of the documents. Otherwise, we keep rewriting and rewriting. So yes. And probably also, I don't see any picture here, so probably there could be pictures here that would be. So yeah. Anyway, the thing that is important to me, at least I'm saving the links, and we know where we can go and get those citations. And I also don't want to give any impression that I'm being comprehensive, because I'm not. Okay, so we now show that the state's capacity recovers a notion of number of cases in all three spaces. In the discrete classical case, it recovers a number of points. In the continuous classical case, it recovers the Liouville volume. In the quantum case, it recovers the number of orthogonal pure states, which the number of orthogonal pure state is actually the dimensionality of the subspace. So in all these three cases, this thing that we devised, that we defined in this general way, actually correspond to something physically meaningful. So the proofs, again, they're not very difficult. So let E be a discrete classical ensemble space, and let U be the subset of essentially the corresponding extreme points, sort of the points on which you are creating the probability distribution, and A be the set of probability distribution whose support is a subset of U. So we're basically taking special sets, and these special sets are just the subspaces of the space. Then the state capacity of A is just the number of elements that are in U. And this, again, the proof is simple. Let A be the set of probability distribution defined over a discrete countable set U. The highest entropy is achieved by the uniform distribution, which equals logarithm of the count of the elements of U. And so if U is an infinite set, that's going to be infinite. Therefore, the state capacity of A is 2 to the logarithm of the count of U, which is the number of U. And again, similar things are going to be happening for classical mechanics. We have continuous classical ensemble space. U is a subset of corresponding symplectic manifold. U is a subset of phase space. And A is a set of probability distribution whose support is a subset of U. So we have a region of U. You take all the possible distribution over U. Then the state capacity of A, the state capacity of all this possible set of distribution, is just the Liouville measure of U, where mu of U is the Liouville measure. And again, you take A be a set of distribution whose support is U. The highest entropy is achieved by the uniform distribution, which equals the logarithm of the measure of U. And therefore, again, you have the state capacity of A is equal to 2 the exponential of the entropy, which is the logarithm of mu of U, and therefore you get mu of U. In quantum mechanics, again, you have something similar. Let U be a subspace of a corresponding Hilbert space, and A be the set of density operators defined on that subspace. So they have 0 eigenvalue outside that subspace. Then the state capacity is the dimension of U, where the dimension is the dimensionality of the subspace. And again, let A be the set of density operator defined on subspace U. The highest entropy is achieved by the maximum Lemming state, which equals the logarithm of the dimension of U. And therefore, the state capacity of 2 times the entropy, which is the logarithm of the dimension of U, so you get the dimension. So all of this works, and it's nice and general. And again, the only thing that I would need to add here is example for field theory, both classical and quantum. I just do not know how to work with entropy in field theories. So if somebody out there watching this video and they know and want to help, I am happy to to have somebody else teach me how it works instead of reading a bunch of papers where most of the time I don't understand what I'm reading. Okay, so this is about state capacity. I can wait 30 seconds to see if there is any question on this. And if there are no questions, then we can start working on the fraction capacity, which is the thing that is going to connect to the probability measures instead of the volume measure in phase space. Ooh. So do we have enough time? I think, yeah. Okay, then let's start. Yeah, this section has pictures, so it's going to be a little bit easier. Okay, so having seen how the strict concavity of the entropy leads to geometric structure, we are going to see how mixing is responsible for the measure of theoretic structure. In the same way we derive the geometric structure on the ensembles, we're going to first define a measure theoretic structure on the ensembles as well. This measure, the fraction capacity, will tell us how much of an ensemble can be seen as a mixture of a set of others. It is not additive in general, but subadditive. So this is the part that we're going to look at today. Then, as sort of looking ahead, we are then going to find necessary and sufficient condition for a subset of ensembles to form a classical probability context, so that each element can be understood as a classical probability measure over a set of cases over a spectrum of the context. We will see that all classical ensemble spaces are classical probability contexts, while in quantum mechanics, the set of mixed state that commutes with a complete set of commuting observable correspond to a classical probability context. So we're going to look at this next time, but the point is that this is how we connect to classical probability, both in the quantum case and in the classical case. So let's start with the fraction of fraction capacity. In this section, we're going to define fraction capacity, which can be understood as a generalization of probability that works with any ensemble space. The typical way to understand probability is through outcomes of a process. 50% for tails means that if we repeated the coin toss multiple times, we would expect roughly half to be tails. In classical mechanics, it can be also understood as a probability of preparation. Roughly half the times we selected a preparation procedure that prepared tails, right? So, you can imagine I'm flipping a coin, or I have two things that prepare always heads and always tail, and then I have something else that switches in between one and the other and gives me the tail or the head, and that's basically the same thing. So you can think it as a probability of outcome or as a probability of things that I'm putting in. Okay, in quantum mechanics, and this is the problem why quantum mechanics is confusing, this does not work, as the probability used during mixing is the same as the probability of the outcome only if we are mixing orthogonal states. So if you take two non-orthogonal states and you mix them, so you make 50% spin up and 50% spin left, and then you go and measure spin up, you are not going to get the spin up 50% of the time. You're going to get spin up more than 50% of the time. So the probability of preparation is not the same as the probability of the outcome. So effectively, probability in the usual sense is defined only on outcomes, right? So when we're mixing things together, that's not really a probability. It's like more of a mixing coefficient. It has some feature of probability, but it's not a probability. And so the fraction capacity instead defines a measure on the preparation. So this is the thing that we are always going to have, that it's the same in classical mechanics and quantum mechanics. We can always take two ensembles and make a mixture. And that's what the state capacity is going to model, is gonna define. It's going to be defined on that mixture. And since the mixtures work the same both in classical mechanics and quantum mechanics, the mixing coefficient work the same, we can get a generalization of something that then becomes probability in special conditions. So the fraction capacity tells us how much of an ensemble E can be constructed through a mixture of ensemble from a set E. It is non-negative, unit-bounded, subadditive, monotone, continuous measure, and it reduces to the probability measure in the classical case and over measurements context in quantum mechanics. The goal is to create a measure theoretic generalization of probability theory that can work on all ensemble space. Okay, that's what we want to do. Now let's see how we do it. So first we define the fraction of one element within the other. For example, suppose the E is a uniform distribution for a six-faced die. So this is our uniform distribution. Suppose A represents the outcome 3 with 100% probability. So this is A. Then E can be understood as this mixture of A 1/6 of the time, and 5/6 of the time we get B, where B is the uniform distribution over the outcome 1, 2, 4, 5, and 6. Okay? So the uniform distribution can be understood as the distribution of a single thing plus a distribution on everything else. Then note that 1/2 is the highest coefficient that we can put in front of A in a convex combination and have E as a result. So we could put instead of a 1/6, a 12th here. And instead of putting the uniform distribution here, we would have the uniform distribution and plus, half here, right? We would still be able to get E from something that is A, like with a smaller coefficient. And 1/6 is the biggest one because, again, probability cannot go negative. So I can't put a half here because here would have to be negative, and that is not going to be a probability distribution. That's the difference between having a convex set and a vector space, a convex space and vector space. So note that 1/6 is the highest coefficient we can put in front of A in a convex combination and have a result E as a result, which coincide with the probability of obtaining 3 from a uniform distribution over 6 outcomes. That is, we define the fraction of A in E to be E. And so this is going to be related to probability because again, for classical distribution, it works like that. And so let E and A be two ensembles. The fraction of A in E is the greatest mixing coefficient for which E can be expressed of a mixture of A. So we take A, we take all the possible combinations, convex combination where one element is A and B, E can be anything, and we get E. We find all the possible P's and we get the supremum. That's going to be the fraction of A in E. How much of E can be understood as coming from A. Okay, so that's the definition. And here there is remark. We need to take the supremum as the maximum may not exist. So again, this is something where we're saying before, we need to be able to be general. And so even here, we take the supremum, not the maximum. For example, consider a discrete classical ensemble space and remove the extreme points. So you take this space of ensembles, but you don't have the extreme points. So you can go and get closer and closer to the pure states, but the pure states somehow it's impossible to get. You're never going to get it. And in this case, then you are not going to get a maximum. You're going to get a supremum. And at the moment, there is no reason to rule out such spaces as physical. So there is a sense that maybe if we had a true theory of Planck scale, whatever, it could be that you could, like this idea of the state that is perfectly prepared might cease to exist. You have a sequence of approximation to something that it would be a pure state, but you never have a pure state. So in that case, then like it would be like saying you can never reach zero entropy. So zero entropy is the limit. You can make approximation that go closer and closer and closer to zero entropy, but you can never get zero entropy. If that's the case, then the boundaries of the ensemble space are open, so you can never get them. And therefore, we can't really just say that there is a maximum. We can say there is a supremum. The supremum is always going to exist. And so that's why we use the supremum and not the maximum. Maybe in 6 months, we'll figure out that can't happen for some reason. And then we'll go back and say, you know what, we can just put the maximum because. But you have to start being conservative. Okay, another thing that is a simple corollary, that the fraction of A with respect to E is 0 if and only if A is not a component of E. And note that if A is a component of E, we can write E as lambda A plus lambda bar B for some lambda between 0 and 1 with 0 excluded. And in this case, then the fraction capacity would have to be greater or equal to that lambda. And conversely, if the fraction capacity is greater than 0, then we can find strictly greater than 0, you can find an element that it's within 0 and the fraction capacity, such that you are going to be able to express E as a convex combination of A and something else by definition. So this is a simple thing. Fraction capacity is 0 only if something is not a component of something else. Now, we want to define the fraction capacity. The fraction was from one element inside one other element, and the fraction capacity of a set of ensemble for another ensemble. That's what we want to define. Like before, suppose that E is a uniform distribution for a six-faced die, but now take A as the set with A and B, and A and B are the outcome 3 and the outcome 4 with 100% probability. Now, E can be understood as 1/3 the equal mixture of A and B plus 2/3 C. So this would be the equal mixture of A and B, and this would be C, where C is the uniform distribution over outcomes 1, 2, 5, and 6. And note again that 1/3 is the highest coefficient we can put in front of any convex combination of elements of A and still make a convex combination that has E as a result. That is, we define the diffraction capacity of A for E to B. That is what, well, it's not that is. That is what we define the fraction capacity of A for E to B. I can't even read well what I wrote, so probably this should be revised again. Okay, so that's basically the idea. You take A, you make all the convex combination, you find the biggest coefficient, that's the fraction capacity. The fraction capacity then defines how much of the ensemble E can be constructed with elements of A. The term capacity is used first because intuitively it tells us how much A can hold, and second because capacity is the name used to describe non-additive measures. So it kind of works in both ways. So the fraction capacity, in fact, has several nice properties. First, its value is always between 0 and 1. We're going to just look at them while we prove them. Otherwise, we just look at them twice. So first, the definition. Let's see. Yeah, that's the second time you use that sentence. It's a bit triggering to try. Yeah, that's why I say the text should be reviewed at the end. So anyway, okay, so let E be an ensemble and A is a Borel set. We just take a Borel set. We could take any set, but at the end of the day, the sets we were interested are going to be the Borel ones. The fraction capacity of A for E is the biggest fraction achievable with a convex combination of A. That is, the fraction capacity is the supremum of the fraction on the hull, again, union 0. This is the same definition that we had seen before for the state capacity. You take the hull of A, which is the set of all possible convex combination. You take the fraction of all those elements. So you have now this big set of numbers. You add 0 in case that set was empty, and you take the supremum. That's the biggest amount of E can be expressed as a convex combination of A. The fraction capacity uniquely define an ensemble. That is, if you have two ensembles and they're different, then their fraction capacity as a set function is different. And again, proof is simple. Note that E equals 1A plus 0B if and only if E is equal to A. So now let A and B be in the set such that they're different. Then the fraction capacity of A for A is equal to 1. And the fraction capacity of A inside B is going to be different than 1. And so the two things are different. Okay? And now we prove the nice properties that are, again, very similar to properties that are for probability measure. This is a set function, and it's going to be non-negative and unit bounded. So it's going to be from 0 to 1, exactly like a probability measure. The fraction capacity takes a subset of E and returns a real value and is therefore a set function. The mixture coefficients are real between 0 and 1. The supremum is a set supremum of a set of numbers between 0 and 1 is between 0 and 1, and therefore the fraction capacity for an ensemble is non-negative and unit bound. It is monotone. Again, if we make the set bigger, the fraction capacity can only increase. The hull is a monotone function. The image of a set through a map is a monotone function. The supremum is a monotone function. Therefore, the fraction capacity is a monotone function. We have subadditivity even in this case. The fraction capacity of E for the set A union B for the union of two set is less or equal to the sum of the fraction capacities. And I think this proof is still decently simple. So let A and B be two sets, and let P be such that E equals E1 plus P bar E2 for some E1 in the hull of A union B and E2 in the whole space. Since E1 is the hull, is inside the hull, we can write it as the sum of two elements of one in A and Y in B for some lambda. Therefore, we have that E is equal P lambda A plus P lambda bar B plus P bar E2, again, where E2 is the part that it's potentially not in A and B. By definition of fraction capacity, we must have that P lambda is the fraction capacity is less than the fraction capacity of A inside E, because again, this is an element of A and this is something else. So this is one of the coefficients that we get when calculating the fraction capacity. The fraction capacity has to be the supremum of all those coefficients. And the same way, P lambda bar has to be less or equal to the fraction capacity of B inside E. Therefore, P, since it's a combination of P lambda plus P lambda bar and P lambda bar sum to 1, then this has to be less or equal to the sum of the fraction capacity. Since the fraction capacity of U of A union B is the supremum of the sets P's for which the expression always holds, we have that the fraction capacity of the union has to be always less, because it's holding for one coefficient. It has to hold for all coefficient, then it also has to hold for all the for the supremum. And so the fraction capacity is subadditive. And then here I do have the proof for continuity from below and above. So again, if you have a final set and you approximate with set from a set of an increasing sets that go to that set at the limit, or decreasing sets that goes to that of the limit, then you have that the fraction capacity of the limit is the limit of the fraction capacity. And these again, if you've done any measure theory or any probability theory, these type of proofs are exactly what they do. So let A be inside, be a sequence of increasing sequence. Let AI be an increasing sequence. Again, we are getting a set of Borel sets because probably those are the only ones that we're interested in anyway, but it could even be subset of the whole space. It doesn't really matter. And it's an increasing sequence because every next set is a superset of the previous one for all AI. Given that the fraction capacity is monotone, then the fraction capacity of the AI is an increasing sequence. And note that the fraction capacity of the AI is going to be less or equal to 1 for all I, because we have an upper bound. Therefore, the sequence will have an upper bound, which will coincide with the limit. This is, what's it called? The Born's lemma or something, Yorn's lemma, something like that. Anyway, it's a general result of order theory. If you have a sequence and you have an upper bound, then that's it. You're going to have a limit. Now, but we have a limit, but we don't know that the limit of this sequence is actually the number. All right. So now we have A being the limit of the sequence of sets. And since A is an increasing sequence, then A is the union of all the AI. And AI, therefore, is a subset. Any AI is a subset of A for all I. Since the fraction capacity is monotone, we have that the fraction capacity of any AI has to be less or equal to the fraction capacity of A for all I, because each AI is a subset of A. And therefore, the limit of the fraction capacity of AI must be less or equal to the fraction capacity of A. Now suppose that the limit of the fraction capacity of AI is strictly less than the fraction capacity of A. then there would be an A inside the hull of A, such that the fraction of A is greater than the fraction of B for all B in the hull of AI for all I. But A is in the hull of A. Then it is the limit of a sequence of convex combination CK for finitely many elements of A. There is a we here for no apparent reason. We then. Okay. Okay. So then we will be able to find a k hat such that the C of k hat is greater than the fraction of that B that for a B, for all B that are inside any subset of A. In the hull of any A. And given that AI is an increasing sequence, there will be an AK that will contain those finitely many elements. And therefore, CK is in the hull of some AK, which is a contradiction because we said that it should be not in the hull of any of them for any I. And therefore, you must have the limit. So basically, you're saying, since you're approaching that limit from below, if those limits were distant from each other, the limit of the set and the limit of the sequence would be different, then you would be able to find something in between. And where is that something, where is that something in between coming from, if not from a sequence of the things that you have downstairs? So you have that the limit commute, and then you can use the same argument just by inverting the order of the sequence. So that's basically what we have. And again, I have a couple other conjecture that needs to be proven. The fact that the fraction capacity is updated over sets whose convex closure are separate. Therefore, it is updated over orthogonal sets. This is something that I think is true. It needs to be proven. And then that you can have sigma subadditivity. That is the fact that we have proven subadditivity for 2, and the fact that we have a continuity from below, it should be able to tell us that then we have a subadditivity for essentially countable unions. And again, in this book, it is claimed that finite additivity plus continuity implies a sigma additivity. There is no proof of that, unfortunately, and I need a proof of that. And the conjecture is that this generalized to sigma subadditivity, and again, it should be doable. So that's basically it. So the idea is that from the axiom that we had before, we can define two things. One is a notion of spread of the ensemble that becomes this exponential of the entropy. And given a set, we can define the state capacity as essentially quantifies the maximum spread that you can get from a set of states in terms of the underlying state where you're putting the spread. And then we have this fraction capacity that generalizes, in some sense, probability, not by looking at probability of outcomes, but by looking at the mixing coefficient, what we have to put in the ensemble. And so you ask, given an ensemble, how much of this example is explained, is reproducible as a mixture of a set of possible ensembles. In very practical term, you get, you have some device that is preparing an ensemble, and then you have a bunch of other devices, and you ask yourself, how much of that can I replicate from these devices by creating something that selects randomly from one or the other with given coefficient, with given mixing coefficient. So that's basically it. And then the trick, the thing that is different what we're doing here and what you typically do is that these measures, both for the measure of volume and measure of probability, are typically defined on the set of states. So if you are in phase space, that measure is defined on the particle states. The measure that we have defined is not defined on the particle states, is defined on the set of ensembles. That's why it survives more, because it's defined on something that it's literally the same thing in both classical and mechanics and quantum mechanics. What we need to do afterwards is generate enough of a mathematical framework that from the ensembles, we define the points and then show that those measures that we had on the ensembles become measures on the points, on the pure states, on the particle states, and that the definitions are exactly the same both in classical mechanics and quantum mechanics. And that's going to be a topic for another time. So I think we reviewed enough for today. And so, as usual, I open up for a question on this and anything else, and that's it. Hmm. Oh, very low-level detail today. Right.
Yeah, I don't have any questions. That was a good session.
Good.
Yeah, nothing jumps out as that all makes sense.
Yeah, and then I'm kind of confident that there are probably gonna be interesting things that can be proven from this generic thing. It's just that right now I don't have a sense. Like as I said, I think that a lot of bounds that people put on entropy and uncertainty should be able to be recovered from this, but or maybe we need first to be able to talk about variables and but anyway. But I do think that this is a strong foundation and because it's so general. So
Yeah, certainly it limits the maximum extent of stuff quite literally. Like you can't go beyond probability 1 or something like that. So
yeah.
that's gonna put bounds.
Okay, if there are no other question or anything, then we'll just stop it for today and go do our things.
Okay.
Going 1, going 2, going 3. Okay, let's do it then. Thank you for following everybody.
Thank you. Bye.
Bye.